So, good morning, everyone. I usually put all the sponsor logos in here, but we didn't get a sponsor slide. But the idea is still the same. When you're in the expo hall, they are paying for a lot of these things. The registration fee doesn't really cover all of the costs of arranging this. So go talk to the sponsors. They will not follow you home. They will not email you until you are in the grave. They're just nice people looking to expand their networks and getting to know you. And you are basically the sum of your professional network. I mean, in a professional sense. I think your spouse probably thinks higher of you than that. But for your employer, you are the sum of your professional network. And knowing other data professionals and some of the sponsors will actually someday maybe help you in your career. So go and talk to them. Tell them we appreciate them so we can be back next year again. I built a session on ACID compliance for SQL Server, and ACID is an acronym that stands for, we'll go through that in a second. Anyone know what ACID is? Like any beginners for SQL Server here? This is a beginner session, but if you're a professional, just pay attention. You might learn a couple of things too. So, ACID is an acronym. It means that transactions, any transaction you do in the database, when you do begin transaction, commit transaction, or if it's an implicit transaction, basically an update, insert, delete, they have a certain set of guarantees, things that the SQL Server engine promises you. So you can think of these things as promises. And the first promise is that the transaction is atomic. Like, you're not going to get anything half-baked. Either it's done or it's not done. If you have 5 different indexes on a table, they are all going to be correct, or none of them are going to be updated, but not halfway in between. So that's the atomic thing. That's the business logic that you write. Then there's consistent, which is the database logic. And that's actually the indexing, sorry. So the atomic bit is the business logic. If you have foreign key constraints, if you have primary keys, stuff like that. The consistency is the database logic. There's a subtle difference, but they're very similar. We're not going to be paying too much attention in this session because these are not things that you can generally do a lot with. Instead, we're going to be looking at isolation. Isolation means that when you are working with data, you are not interfering with other people and they are not interfering with you. And finally, the durability. When SQL Server says something is done, I've saved your work, I've committed your transactions, you should be able to trust that. That is, in a sense, that the transaction is durable. I'm Daniel Hotmacher. I won't make you pronounce my last name unless you're Swiss. I live in Sweden. I've been a SQL Server developer for more than 25 years. I do consulting. I organize Data Saturday Stockholm and a lot of other things to give me brownie points with Microsoft, who for some reason have made me an MVP. I still can't really get over that. I'm also a dog person and available on social media if you have comments or heckling. For the record, if you have questions, if there's something you're not keeping up with, ask me, interrupt me anytime during the session. I will repeat your question and try to answer it. There are different types of questions. There are very, very few dumb questions. There are some good questions, and there are some great questions. And the great questions are the ones that I have a slide for later on, right? But interrupt me. Don't keep it a secret to yourself because someone else is wondering too. So I'm going to skip right to isolation. So isolation manifests itself in SQL Server in different so-called isolation levels. You can define an transaction isolation level when you connect to the server, or you can change it while you're connected. And this defines, think of it as a visibility SLA or a promise from the engine. Like, what can you do in the database? And we'll get to how this maps out across different isolation levels and how they behave differently. The first one is read uncommitted, aka the no lock. Who knows no lock? You've all seen it. You've all put it in your databases. I've seen your databases, yours too. So basically, if you think of the green arrow here as a transaction, the transaction is running an update. You begin transaction here, over on the left. You do an update, and I'm trying not to fall off the stage. And then over there, you're going to commit the transaction. But while you're doing an update, someone goes with read uncommitted isolation level or a no lock hint and does a select query. What will happen to that select query? It'll just run. It'll just show you whatever is happening in the table right now. Could be true, could be false. It'll show you some uncommitted stuff. Worst case, if you're moving rows around in the index, you might see the same row twice, the old row and the new row. No lock is dangerous. You all know that. You don't need the lecture. What you see when you're seeing uncommitted transactions are called dirty reads. So essentially, you're seeing stuff that isn't finished yet, hence dirty. If you level up to the next isolation level on the scale, this is called read committed. And as the name implies, read committed means you can see only stuff that has actually been committed. If there's a transaction going on, you will be left waiting for that transaction to finish before you can look at the data. And that's when blocking happens. So you get to see the truth as opposed to work in progress, but instead you have to wait for it, which makes sense. No locks work for select queries, but not for update queries, because obviously you can't update something that doesn't exist, if you will. So read uncommitted works if you're doing select. If you're trying to make updates, inserts, delete while you're in read uncommitted, it will revert back to the read committed isolation level, and you will be blocked and wait for the other transaction to finish. And here's sort of the timeline for that. If you have a running update and you try with read uncommitted to update that, it will just wait because it doesn't really apply to updates. Demo time. Can you all see the screen? Is it big enough? Take that as a yes. And I have two sessions, one on the left, one on the right. Those are the same database, same server. I'm going to create a table, call it account table, bank statement or whatever, bank balances. On the right-hand side, I'm going to go to read uncommitted using the set transaction isolation level command. This could as well be a no lock hint, but just for clarity. Now I'm going to transfer money from Brent's account to Katrine's account. And to do that, because we want the atomicity, I'm going to begin transaction. I'm going to reduce Brent's account by 100 money units. And I'm going to check on the accounts. I did them in the wrong order, but that doesn't matter. If I select in the right-hand query, which is in no lock or read uncommitted, I can see my changes. Remember, I haven't committed the left-hand side yet. This is an ongoing transaction. You're literally, this is the microsecond on your online banking app where you pressed transfer. It has taken money from one account and it's about to put the money into the other account, but the transaction is still open. But the right-hand side session uses no lock. And so we can see that money has been withdrawn, even though we shouldn't. This is a dirty read. What happens if we update? If I try to reduce Brent's account by more money? Anyone remember? Get blocked, right. So you see the query is just waiting for something to happen. Time progresses. And now we're going to insert that money into Katrine's account. There, money is in her account. Watch for the right-hand side when I commit the transaction. As soon as that transaction commits, this update can run. Because the update runs in read committed, because you cannot do data changes in read uncommitted. There are edge cases. For instance, if you're reading from one table and updating another, the read can still do a read uncommitted. So the next level up, the next isolation level is slightly more restrictive. It's called read committed. We mentioned it briefly. Read committed means you can see anything at any time as long as it's already committed, as long as it's not work in progress. This is like the bare minimum standard. This is what Management Studio and Azure Data Studio default to when you connect to a new server. Unless you explicitly specify it, this is the isolation level you're getting if you didn't know it. So if you have a transaction at the bottom, you can select data and someone else can update that data, and you're still in the transaction below, and you can select the same rows again, and you might get a different result. But you're not getting work in progress. You're not seeing the changes as they are happening. You see them either before or after they happened. That make sense? Right. If you're worried about seeing the same data change over time and really not knowing what's going on, the next isolation level up from that would be repeatable read. So that would be the fix. Repeatable read is the third isolation level. What happens if you have repeatable read? Remember how I told you isolation levels are promises? SQL Server in repeatable read will promise you that reads are repeatable. So if you look at something, that is a promise SQL Server is going to keep. The data won't change on you. What that effectively does is, first time you select the data, it places a lock. It says, someone's looked at this information, so now it mustn't change unless I commit or roll back this transaction. Like, because I have to guarantee to my user that this information is the way they saw it. And so the update would be blocked and wait for the transaction to finish. This is going really well. That's what I always say before I jinx my session and everything crashes. I'm going to go to read committed. And I'm going to begin a transaction on the right-hand side. I'm going to look at the accounts. You can see that Brent has 100 units. Now in the left-hand side, I'm going to update. Did I? Yeah. So in the left-hand side, I'm updating the balance. And now if I go here, on the right-hand side, in the transaction in read committed, I'm going to see that change, even though I'm still in a transaction, right? So I'm going to roll back that transaction. I'm going to go up, set it to repeatable read. Begin transaction. Let me see if roll back here and cleaning out the table, so we start over from 0 again. Now, I set repeatable read on the right-hand side. I begin my transaction. I look at Brent's balance. He has 100 units. I go to the left. I update his balance. And it's stuck waiting, because I've promised the right-hand side user that the balance is 100 units. So you can't change it until the right-hand side says, okay, I'm done with this. I'm going to proceed down here. I'm going to do another select just to see that the balance is unchanged, as we expected. And then I'm going to roll back. And when I roll back, I close the right-hand side transaction. The left side can finish. Because repeatable read guarantees that what you've read can be repeated. You will see the same data in the same slots. Asterisk. So who knows what phantom reads are? Cool. This is going to be fun. So imagine the scenario we had just now, where you select data in a transaction. Say it's repeatable read. You do a select, you look at all the balances, someone goes and inserts a row. And then you do another select. Now, repeatable read will guarantee that data hasn't changed. It doesn't really check for if data has been added, right? So if it was there, Repeatable read will guarantee that it is still there and the same, but it doesn't guarantee that there isn't other data. Because it's a technical issue, really. It's hard to lock rows that aren't there, right? If you're walking into a restaurant in Sweden, we have this annoying habit of paxa, which basically means you put your jacket on a chair and now it's yours, and now you can just walk away and do something else, go order food or whatever, and when you come back and everyone will magically respect that this chair is yours. Same thing goes for locks in SQL Server. If you put your jacket on a chair, it's yours. That chair being the row that you looked at, because you know that it's going to be repeatable. But how do you lock a chair that isn't there? How do you say, like, I'm going to sit here when there eventually will be a chair? Or I want to make sure there's no chair ever being moved into this slot, right? And that's what the next level, which is called serializable, protects us against. Serializable is an isolation level that not only locks specific items, in this case, it will lock a range, right? So if I select data, if you try to insert data somewhere in that range of data that I've selected, serializable isolation level will place a range lock between two keys, two rows, and say nothing must change between these two rows, which is kind of weird when you think of it, but it makes sense. And the effect is that the insert will be blocked and wait for the transaction to commit. If that makes no sense, I hope it will after you see the demo. A question? So the question was, repeatable read doesn't sound like a really smart idea because it will block, it will block other DML commands, i.e. changes. And that's, if you think about it, there's a trade-off in a multi-user database where you want to allow multiple users to work with your data, but you also want the data to be consistent. You want to know you want it to be predictable. So say you're withdrawing money from one bank account and depositing in another bank account. You want to know that that target bank account is still there when you go looking for it. And so these isolation levels, and there's a slide coming, so this is an excellent question. These isolation levels offer varying degrees of protection from changes and unexpected outcomes, where you can go from the most concurrency and the least reliability to the most reliability and the least concurrency. So if you've done traditional programming, you know that serializing an operation is when you put one thing after another, essentially single threading all of the stuff that comes into the database. So serializable is the most restrictive in that sense. I hope that answers the question. So I have another transaction table on the left-hand side. I'm going to go to repeatable read on the right-hand side. I am going to begin a transaction on the right-hand side, and I'm going to look at all of the balances for people whose names begin between B and D, right? So you have Brent, who has 100. You have Katrina, who has 100. I'm going to insert Claudio, who I think is actually in the next room. Not intended, but that's how it panned out. Now what will I see? I have repeatable read, right? What will I see when I run the right-hand side query? Claudio will magically appear. Yes, there he is. He has $1,000 actually. Lucky Claudio. I will come to the question right in a second. If I roll back the right-hand side, I reset the left-hand side. And this time on the right-hand side, I will do serializable. So serializable, remember, being the most restrictive isolation level. I'm going to begin a transaction. I'm going to look for B through D. Then I'm going to insert Claudio. And we're blocked. Because now, with the serializable isolation level on the right-hand side, I am guaranteeing consistency. Like if you've looked in the database, you are sure, asterisk, that next time you look, you will get the same outcome. You will get the same result. So the right-hand side has no information about the stuff that's being blocked in the left hand. When I check again, same information, still just Brent and Claudio. I roll back the right-hand side, and Claudio is added. Brent and Katrina, I meant. And now Claudio is there as well. Yes, your question. What is the proposed or best isolation level for an transaction-intensive OLTP environment? I would say, and this is a cop-out answer, it depends. It depends on how important your data is, and it depends on how the data is updated. If you're doing banking transactions, I think you're probably stuck in serializable, because there's no way you're going to explain to the customer, like, I thought you had a balance on your account, and then we paid the bill, and now you're in debt to us, or something like that. Whereas if you're doing data warehousing, read committed will probably be just fine. I personally, and I think there are other people who feel strongly about this as well, I personally don't think there's a use case for no lock, unless you're doing debugging and looking like, how far has my update come, what's going on really. So the answer is, it depends on your use case and what your load looks like, essentially. Good question. We're moving into the fun stuff. So here's a summary of what we've talked about. We have read uncommitted all the way on the left, which means you can see anything, whether it's committed or not. It's just a mess. You can see duplicates. Rows can be missing. You can see incorrect results. You will very likely see stuff that someone is going to roll back. And notice the arrows at the bottom. To the left is less likely to block, but more concurrent. Anything goes, right? Anything, just get in there and do whatever you want. Whereas on the right is serializable, which is more likely to block, but less concurrent. So it's a stricter isolation level. It's more isolated, basically. Read uncommitted comes with dirty reads, seeing stuff that isn't committed. It comes with non-repeatable reads. You query, and then you query again, you get different results. And it comes with phantom reads, which is basically you query the data, next time you query, something appears, a phantom. Read committed fixes the dirty reads. Repeatable read fixes the non-repeatable reads. I think you're with me on that. And serializable finally places those range locks which prevent phantom reads. Yes? The question was, the range lock is not actually a table lock, is it? Yes. So the range lock picks two keys in an index or a heap or whatever, and it locks everything between those keys. So basically, it's preventing you from inserting data between two keys, because you can't lock something that doesn't exist. So if you have B and D, a range lock will lock everything between so that you cannot insert C, but it's not a table lock. It is based on the where clause when you're looking at the table. So whenever you look at the table, you're touching the data, and that defines sort of where the lock is placed. Yes, question? Great question. Snapshot isolation is coming up. All right. So serialize all the things then, right? Perfect consistency, everything's going to be great. I want to say that this is probably what some people did until they ran into a lot of issues. So again, the less strict isolation levels will give you much more freedom, much less blocking, but it's less predictable. You don't really know what you're going to get. This is the box of chocolates isolation level. On the right-hand side, better isolation level is more consistency, but there's going to be a person at the door checking ID, letting one person in at a time, essentially, right? So there's no perfect answer for this question. You will have to try it for your workload, and you'll have to let your business requirements decide what kind of isolation level you need. At the bottom, there's also I mean, whenever you have a multi-user system, you're going to run into deadlocks. If you run into a couple of deadlocks now and then, this is a feature of a multi-user system. It's not a bug. It's not a problem with your code if it only happens now and then. If you get deadlocks all of the time, you need to revise your code. But if it happens now and then, there's not a problem. It's the simple truth that multiple applications will update the same data, and sometimes you run into conflicts. So what is a deadlock? Anyone know? Yes, you've all had them. Imagine, if you will, again, the bank account example. So we're withdrawing money from account A. We're reducing the balance on account A. We intend on putting that money in account B. Meanwhile, in another transaction, someone is already withdrawing money from account B. What happens in SQL Server is now you're placing locks on these things that you've changed. So we've locked actually account A, and we've locked account B because we've updated the balances. We don't want anyone else to be messing with it, right? Now transaction 1 wants to deposit the money from account A into account B. But account B is already locked because someone else was in their internet banking application, which means that transaction 1 is going to be blocked. Transaction 1 will wait for transaction 2 to finish. Meanwhile, transaction 2 wants to deposit the money into account A. So transaction 2 is going to be blocked by A, and transaction 1 is going to be blocked by, well, they're blocking each other, right? This is what's called a deadlock. And SQL Server, because this, as I mentioned, this is a natural occurring phenomena in a multi-user system, even non-database applications see deadlocks. When you're trying to allocate memory on your Windows or whatever, you can run into deadlocks. You just never see them as users because there's retry logic behind the scenes. But it happens in every multi-user system, everywhere where there's concurrency, where two resources can compete, where two processes compete for the same resource. What happens is SQL Server's way of cleaning this up, it has like a night watch guard patrolling the area. So this agent, I forget the name now, patrols the SQL Server databases, looking for blocked threads that are blocking each other. And when it finds one, if it finds a deadlock, it's very, very pragmatic and unsentimental about it. It will find that one transaction has done the least work, that is the easiest to roll back, and just kill that transaction. It'll roll back that transaction, and the user will get the famed, is it 1251 or something like that? Error message, 1215? Looking at the DBA. 1205, thank you. And the user will get the famed error 1205, which basically means your transaction was deadlocked and chosen as a victim. Retry the transaction. And if you read the message, it says, retry the transaction. There was nothing wrong with your code. You just need to do it over again. And so if you're really careful about writing well-behaving, high-performing applications, you build in retry logic that looks for that error message and retries the transaction if you get a deadlock error. Yes, question? How to avoid deadlocks is outside of the scope of this session. But long story short, if you look at the logical flow of how these things happen, if you write more performant code, the shorter time you hold your locks, the less likely you are to cause deadlocks. So it is a performance issue in one sense. But also, if you look at the order, if you were to lock A and then B and then C, if you go alphabetical or in some deterministic order when you lock the transactions, they will actually chain each other. They will become serializable effectively. So in this example, if you had locked transaction or account A in transaction 1 and then account A in transaction B, B would be waiting for A, and then you could complete transaction 1, and then transaction 2 could complete. So lock in the same order, optimize your code. That's the short answer to the short question. But this is a hard problem to solve. That's why just making sure your query doesn't run forever and adding retry logic is often the best approach. I have a demo for this. You won't believe it. True story, I was presenting this session somewhere else, and the internet crashed. So I had to run it in a different environment, and I ran it in an environment where I could not reproduce deadlocks. The DBAs among you will know what happened. So I'm going to go back to read committed isolation level, which is the SQL Server default, the Management Studio default. I'm going to go to read committed on the left-hand side. The process is simple. This is, I begin transaction, I update Brent's account. I always take money from Brent for some reason, and I put that money into Alexander's account. And on the right-hand side, Alexander is actually in a very good mood today, so he's going to take money from his account and give to Brent. So let's go. Begin transaction. Begin transaction. Alexander reduces his account balance. Brent reduces his account balance. One process has locked Alexander's account. One process has locked Brent's account. Now, on the right-hand side, we're going to insert that money into Brent's account. But we're working with Brent's account, so we're busy. That account is locked. That row is locked. So we're waiting for something to happen. And now we're going to add money to Alexander's account. Now they're waiting on each other. And this night watch thing, background guard agent something, deadlock agent, is that it? It checks every 7 seconds. So it doesn't check millisecond because that would slow your system down. It checks roughly every 7 seconds. So you might get this error immediately or anywhere between 0 and 7 seconds from now. So you can see that the left-hand side started all this, has done the least in some sense, and that was chosen as the deadlock victim. And you can see that this transaction, process ID 87, was deadlocked on lock resource, blah, blah, blah. You can even see what it was deadlocked on. And technically, it doesn't have to be a row in a database. You can be deadlocked on anything, memory allocation or whatever. The right-hand side knows nothing of this. It can commit its transaction and we're good to go. There was a question. Yes, you can set, can't we set deadlock priority in this case was a question. In SQL Server, I believe you can set a deadlock priority on your queries, so you can decide, like, if I get into a deadlock, am I going to win or am I going to lose this fight? Typically, in my experience, you have very similar queries deadlocking each other, like OLTP-style queries where they are like this. You're moving money from one account to another, right? And so which one of these would you put a higher priority on? But this is not always the case. So again, it depends. But good question. Are your brains fried, melted, or you want more? Because I have a really weird problem I ran into in an actual client case, and I'm going to see if you can see what actually happened. Imagine I have a table. It's a clustered index, no other indexes. I have the rows that are inserted are A, B, C, D, and E. This is the data that exists in the table. Now, I'm using a Kafka sync, which is an event stream type of application, to stream data into this table. I'm loading this table with a couple of different, they're called syncs, but basically insert processes. The way the Kafka sync does this is it uses a merge statement. I know, as the designer of the solution, that all of the rows will be new. There won't be any conflicts. But because the pattern uses a merge statement, the merge statement goes and checks if the row exists. If it exists, it inserts it. If it doesn't exist, it updates the if it exists, it updates the existing row. If it doesn't exist, it inserts the row. There's row 1 for B1, and then there's B2. And if you've read Aaron Bertrand's blog post about merge comes with a couple of tricky issues, and there are split opinions in the SQL community whether you should use merge at all. I'm a fan. I like merge when used appropriately, but I would argue that it is a bit of an unfinished feature. There are a couple of bugs that Microsoft has just plain said, we're not going to fix these. So one of the fixes for that is to apply a hold lock hint to the merge statement, which forces a serializable isolation level. And that's what we're doing here. Why am I getting deadlocked when I'm inserting two rows that don't exist? So the guess was we scanned the table to see if the rows exist, but the table has a unique clustered index. So we would actually just have to see exactly if that row existed. But I'm not going to spoil it for the others. So I actually have a demo for this. This took me a while to figure out, because I've given you more hints than I actually had when I tried to solve this problem. Let's go to serializable. And serializable. Here's what the original merge statement looked like. So merge into deadlocks using a list of hard-coded values. When not matched, insert. When matched, update. Simple enough, right? The average performance of this was like a fraction of a millisecond because we had a lot of data coming in, absolutely streaming in data. So to make this demoable with anything less than 1 million transactions streaming in a couple of seconds, I've reconstructed the merge as basically a transaction. These are the values I want to insert. I'm going to begin the transaction because the merge statement runs in an implicit transaction. I'm going to check if the row exists. Then I'm going to introduce an artificial weight to simulate sort of the milliseconds or fractions of milliseconds. If the row exists, I'm going to update it. If it doesn't exist, I'm going to wait for 10 seconds, again, to simulate a slow system. And then I'm going to insert the row instead. End and commit. So this is basically a manual merge statement that I've written. I'm going to prepare that on the right-hand side as well. These are exactly the same. So I'm running exactly the same commands, but I promised you that the rows would be unique. So on the left-hand side, we have Brian. Bear with me. On the left-hand side, we have Brian. And on the right-hand side, we have Brian 2. So there are two different usernames, I know. I'm going to run this. I'm going to switch over to this. I'm going to run this. And it'll take 10 seconds because I introduced the artificial delay. Seconds is a lot of time. And I get my transaction deadlocked, just as I got in the client environment. Now, it turned out the root cause of the problem, and you were close, you were very close, was the first transaction looks if there's a B1. The second transaction looks if there's a B2. What effectively happens is I'm creating a shared range lock. A shared range lock means I'm protecting this data so that nothing changes, but others can still look at it, right? So I'm sharing. I'm not holding this as my own personal secret. I'm sharing everything, but you can't change it because I have dibs on it. Now, B2 does the same thing. It applies the same shared range lock on the same place in the database. Now, both processes are holding shared range locks. By this time, B1 has figured out that that row doesn't exist, so we're going to insert it. What happens when we insert a row? We need to upgrade that lock to an exclusive range lock. Now we're going to actually do some damage, so we can't have a shared lock. We need to have an exclusive lock. But we can't upgrade the exclusive lock to an exclusive lock until B2 has left the shared lock, because exclusive is really exclusive in that sense. Now these two are waiting for each other, even though they're separate rows with separate IDs, and they're going to deadlock. Viewed in a different, oh, this is snapshot isolation. So what was the solution? How did I fix this problem? Just checking, see if you're awake. Sorry? So Hugo suggested adding exclusive locking, and because you're you, I'm not going to say you're wrong. I don't know. That's not what I did. I convinced my customer that because you're always getting unique rows and you don't meet the criteria where those bugs appear for the merge statement, and there are like 16 of them from Aaron Bertrand's blog post that I checked. None of them applied to my case. I said, why not just go to read committed, right? Because you're guaranteed by the delivering the source system that the rows are going to be unique. So you're not going to run into any of those issues. Worst case, the insert fails and would be none the wiser. So changing the isolation level to read committed by just removing the hold lock hint solved the issue. I feel bad for the developers because the Java people had to actually take the sync code and recompile it without the hold lock hint, so I hope they knew what they were doing. Questions on deadlocks? Yeah. So the question was, in the demo, the first transaction was determined to be the victim of the deadlock as opposed to the second one. And because it was started earlier, it should have progressed further. It was started earlier, but it had progressed exactly the same amount. So I think when there's a tie like that, and now I'm riffing, I'm guessing, when there's a tie in how much work has been done, I think SQL Server picks the oldest transaction. That's my guess. You can see transaction deadlocks basically as non-deterministic. A deadlock can happen anywhere, anytime. All right. So snapshot isolation. Someone asked about that before. Snapshot isolation is a new within air quotes magic. It's only been around for like what 10, 15 years now. What SQL Server does in snapshot isolation is, I think it's basically magic, and this stuff comes on by default if you're in Azure SQL Database or any of the other cloud services. I'm going to clarify, there are two different types of snapshot isolation. I will return to that later. If you do a select in transaction 1, SQL Server will remember what the data looked like when you did that select. When you looked at the data, SQL Server will remember that until you let go of the transaction by committing a rollbacking. Transaction 2 looks at the data. Transaction 1 updates the data. But SQL Server remembers what version 0 looked like. So when transaction 2 looks again, the data is going to be the same. And these are non-blocking. So, and then transaction 1 commits the transaction, which basically upgrades the version 0 to version 1. And then as we've committed transaction 2, we've released sort of that memory. And when transaction 2 looks again, it's going to be version 1. The takeaway is, if you look at something with snapshot isolation, SQL Server will remember what it looked like last time you looked until you're committing your transaction. Then all bets are off. But for the duration of your transaction, SQL Server will remember what the data was like the first time you looked at it. I was going to make an analogy to love or something, but you get the idea. So this introduces a whole new set of rules for us. Well, actually, it doesn't. Because it remembers what the data looked like when you accessed it, there are no dirty reads. You can only see committed stuff because you saw what was committed when you queried it. You don't get non-repeatable reads because the data doesn't change. It's versioned. It's versioned for you. You have your version that you see implicitly. And there are no phantom reads for the very same reason. But what about deadlocks, I hear you ask? Well, deadlocks are tricky. Deadlocks happen when two processes try to update the same thing, right? They can happen for snapshot isolation transactions as well, but it's not called a deadlock. It's fundamentally just slightly different, and because of that, we call it an update conflict. And we're going to look at that in a demo. Oh, we're going to look at some slides. So imagine, again, transaction 1 does a select. Version 0, it updates, but it's still in the transaction. It's still locked, right? Transaction 2, meanwhile, has done a select. Transaction 2 sees the versioned information. Transaction 2 sees version 0. Transaction 2 wants to update the same information, which brings us to version 2. Now you're committing transaction 1, but now that you're trying to commit transaction 2, you get what's known as an update conflict, because this doesn't make sense. You were promised that you were on version 0, and now you want to go directly to version 2. And that doesn't make sense. That's where you run into an update conflict. I only got half of your question because of noise, but I think it was, shouldn't transaction 1 have put a lock on them? And the answer is no. So because we're in snapshot isolation, it's very optimistic in a sense that it'll probably be fine, right? So we're just showing the snapshot version for transaction 2. I'm going to hold the question because I have a bit of my presentation left. I'm going to skip the update conflict demo. Look me up afterwards. I'll be happy to nerd out and show you because I'm late. There are two different types of transaction isolation, snapshot isolations in SQL Server. There's one read committed snapshot isolation, which is a database setting. Read committed snapshot isolation is what you get in Azure SQL, Azure SQL MI, all those things. You can turn it on in SQL Server on-prem, but you need to explicitly turn it on per database, and that starts the versioning. Snapshot isolation is an isolation level that you choose with set transaction isolation level. They behave very similar, but there are some differences. Snapshot isolation, you set, and it protects the transaction, whereas read committed snapshot isolation, like read committed, protects every statement by itself, right? Again, I'm running a little late, so I'm going to speed things up. That's basically what I have on isolation levels. I'm going to touch on durability really, really quickly. This is how the transaction log works. The transaction log keeps track of everything, all of the changes you make in the database. When you make a change, the process is you place locks, like I'm going to change this row, hold my beer. You read the data up into the buffer pool, or memory as it's known to normal people. You make whatever change you're going to do in memory. You write that change to the transaction log, which is called hardening. And then you release the locks and say, I'm done. The traffic lights signal what we're telling our user. Like the SQL engine says, working, 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 done, right? And sometime in the future, this gets written to the data file of the SQL Server. So durability, SQL Server wants to guarantee you that if it says something is written to the data file, you should be able to trust that, right? If you're unable to load data to the buffer pool, the SQL Server crashes, someone pulls the power plug, nothing happened, nothing's changed, right? We're still durable. No promises have been made. If we can't make the change for whatever reason, nothing happens, promise is still intact. If we can't harden the log, the transaction crashes, disk is full, whatever, no changes have been made, no promises have been made. If we can't release the locks, well, the changes have been made, I suppose. I don't know if this could ever happen. There's probably an edge case somewhere. If we can't write the logs to the data file, then it'll happen later. Which brings us to delayed durability. This part here is the isolation, right? And this part is the durability. We commit to promising the user that the transaction is durable, and the user can trust us on that one. Except if you enable a setting in SQL Server that's called delayed durability, which skips the log hardening bit, or actually delays it. So instead of hardening the log immediately, which usually happens for every transaction, even if you're inserting just one byte, we'll just do that later. This is the procrastination mode. We'll just release the logs immediately, tell the user that the logs are, you're going to be fine, basically. And then you harden the logs asynchronously. And so you see the gap between the isolation and the durability here. We've promised the user something that we will do tomorrow, pretty much like I promised my wife I will start the dishwasher. and then we'll asynchronously write the data, right? But this is the danger zone. This is where if you pull the plug from SQL Server, the data is lost. You've promised the user that the data is committed, but it's lost in actual fact. This is a great pattern for very specialized cases where you can just lose and recreate the data. Staging databases, loading a data warehouse that you can just do a full reload as the server crashes. TempDB actually runs with delayed durability under the hood. It's time. I was going to do some key takeaways, but I didn't. I've worked a lot on all of my presentations. I really, really want to know what you think. So please take your time to do some feedback. It means really, really a lot for me. And also, Monica said that SQL Bits is giving money to charitable causes, including dogs, and I'm a dog person, for every person who leaves a review. So if you think it sucked, if you think it was great, please leave a review. I'm going to be here all day today, all day tomorrow. I am approachable. Just come and ask me questions. I'm here as long as you want. Thank you so much. Almost. And if stream is still on, I can take the question from the screen. You threw it away. That was a dumb question. Yes, so the question was, doesn't TempDB grow considerably with Snapshot or RCSI? Yes, because those versions are stored in TempDB. So if you have a transactionally very intensive system, all those changes are temporarily moved into TempDB just for the versioning. If you have low traffic, like data warehouses don't see a lot of changes, for instance, those things will hardly affect TempDB. So the correct answer is it depends. Yes, so with accelerated database recovery, those versions are stored in the database, not TempDB. That's correct. But it still incurs an extra write. So you have, the table becomes wider and there's more writing going on, but instead you get less blocking.